on Finding Zeros of Polynomials worksheet. So on the front side we found all of the factors, and we split it into the list of all the factors that multiply together to get the original polynomial. Now we're ready for the back side, where the instructions ask us to find all the zeros. And so by zeros, we're looking for what are the values of x that will make this equation equal 0, or that will make each of the factors equal 0. So we're given one factor, x minus 2, and so we want to use synthetic division to break the original polynomial down into a smaller polynomial. What can we multiply by x minus 2 to get x to the third minus 8? So first step is we want to write our original polynomial with all of its terms. So that my leading term is x to the third, so I need all of the terms that have a smaller degree. So I don't see any x squared, so I have to put in 0x squared. I don't see any x's, so I need to put 0x. And I need a constant, minus 8. So I want to take the coefficients from each of these terms. It's 1x to the third, 0x squared, 0x, and negative 8 is the constant. In front of that, I want to put this 0 that I'm given. Well, what I'm given is the factor, x minus 2. So the 0 is what number will make that equal 0. And so if we add 2 to both sides, I see that x equals 2. So my 0 is 2, and I've got my polynomial here. First step is to bring down the 1, then multiply it times the 0, so 2 times 1 is 2. Add coming down, 0 plus 2 is 2. Multiply 2 times 2 is 4. Add coming down, 0 plus 4 is 4. Multiply that by 2. 2 times 4 is 8. And then add negative 8 plus 8 is 0. That final 0 tells me that x minus 2 is a factor, that 2 is a 0 of this polynomial. And so what I'm left with, the original term was x to the third, so when we took out x minus 2, this is now 1x squared. It's 1 degree smaller. So this becomes 2x, and 4 is the constant. So one approach here would be to try to factor. But what I noticed very quickly here is that this polynomial does not factor. And so my next alternative is to use the quadratic formula. So that is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So a is 1, b is 2, c is 4. So quadratic formula says x equals the opposite of the b value, which is 2, plus or minus the square root b squared, so 2 squared minus 4, times a value is 1, times the c value, which is 4. All over 2 times the a value, which is 1. So as I go to simplify this, I get the opposite of 2, negative 2, square root, 2 squared is 4, 4 times 1 times 4 is 16, and 2 times 1 on bottom is 2. So I see negative 2 plus or minus square root of negative 12. 4 minus 16 is negative 12, divided by 2. So I've got a square root of a negative number, which means that I need to use I in this problem. And so as we go to the next step here, I want to take out the I, the square root of negative 1. So negative 2 plus or minus square root of 12 times square root of negative 1. Now square root of 12, are there any perfect squares that go into 12? Think 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. Do any of these go into 12? Well, 4 does. So I want to separate this into square root of 4, and 12 divided by 4 is 3. I've still got my square root of negative 1. And so I've got negative 2 plus or minus, the square root of 4 is 2. Square root of 3 cannot be broken down anymore, so I leave that as square root of 3. Square root of negative 1 is I, all over 2. And so then I check the 3 numbers that are outside the square roots. Negative 2, 2, 2. Can those all be divided by the same thing? They can be all divided by 2. So when I divide the denominator by 2, I get 1. And we don't have to write a denominator of 1. So what I'm left with is x equals negative 2 divided by 2 is negative 1. 2 divided by 2 is 1. So I can just write the square root of 3i. And so these are the other 2 zeros. And so as we list out the zeros, the original 0 that we were given was x equals 2. And now I have negative 1 plus square root of 3i, and I have negative 1 minus square root of 3i. So I found 3 zeros, and my original problem was an x to the third. Third power tells me that I'm expecting to find 3 zeros. Example 3 is now finished. Let's look at example 4. In example 4, first step, I want to write down, make sure that I have all of the degrees here. So if n to the fourth is the largest degree, the leading term, do I have n to the third, n squared, n to the first, and a constant? Which I have all of those. So I'm ready to write down the coefficients of each of them. So n to the fourth is 2. N to the third is a coefficient of negative 1. N squared has a coefficient of 8. N has a coefficient of negative 9. And the constant is negative 90. The 0 that we're given, in this case we're actually given the 0, not just the factor. So negative 2 is our 0. If it had an x in front of it or an n in front of it, that would tell me that this was a factor. But when it's just a number, that means it is a 0. So, synthetic division, bring down the first number, and then multiply 2 times negative 2 is negative 4. Add coming down, negative 1 plus negative 4 is negative 5. Multiply negative 2 times negative 5, positive 10. 8 plus 10 is 18. 18 times negative 2 is negative 36. Negative 9 plus negative 36 is negative 45. Negative 2 times negative 45 is positive 90. Negative 90 plus 90 is 0. Because it came out to 0, we know that negative 2 is in fact a 0 of the original polynomial. So this took out, we started with n to the fourth, we took out one of the zeros, which means we're now left with n to the third. So this is 2n to the third minus 5n squared plus 18n minus 45. So we just decrease the degree with each of the terms. So now we're not given any other zeros, and we still have a n to the third power. So what can we do in this case? Well, our only technique that we have, we look for greatest common factors, which I don't see any. So then I want to look for factor by grouping. The first two terms both have n squared, but the 2 and the 5 I can't do anything with. So I bring n squared in front, and I'm left with 2n minus 5. The last two terms, 18 and 45, can both be divided by 9. So I want to pull out a 9, and I'm left with 18 at n divided by 9 is 2n. Negative 45 divided by 9 is negative 5. And fortunately for us, those two parentheses have the same factor. So I know 2n minus 5 is a factor. And I also am given that n squared plus 9 is a factor. Now, to find the zeros, I need to set each of these equal to 0. Well, first of all, I guess I see that there's an exponent, n squared plus 9. Can I factor n squared plus 9? Well, with two terms, it has to be subtraction in between, so I can't factor that one. But let's try to solve that one just by using it as it is. So, finding our zeros, 2n minus 5 could equal 0 by adding 5. And if 2n equals 5, divide by 2, and we find that n equals 5 halves. So that's one more 0. N squared plus 9 equals 0. So at this point, it doesn't factor, so we could use quadratic formula. But the other method that is mentioned on the front is the square root property. Only works with a quadratic with a missing b term. It has ax squared and it has c, but it doesn't have the bx. Which this one fits that situation because it's got n squared, it's got its constant, but not just n. It's missing the middle term. So in this case, the way we can solve this a little faster than using quadratic formula, or perhaps a lot faster, is to solve for n. So the first step is to get rid of the plus 9 by subtracting 9. And so we find that n squared equals negative 9. Now the opposite of squaring a variable, the opposite of squaring something, is to take the square root. And so if we do the square root of n squared and the square root of negative 9, we're left with n on the one side. Now, one of the things we have to be careful about is because when you square a positive number and you square a negative number, both of those answers will be the same thing. And so we have to account for both the positive and the negative answers when you do the square root of both sides, when you're trying to get rid of a variable that's squared. So as we try to simplify square root of 9, we know that we're going to have a positive and a negative version. And I see a negative inside the square root, so I want to separate that negative 1. And what we're left with is square root of 9, which I know the answer to is 3, and square root of negative 1 is I. So the other two zeros are positive 3i and negative 3i. So as we go to list the zeros as our final answer, we were given -2 as one of our zeros. We found 5/2 is one of our zeros. And now we found that positive 3i is a zero and negative 3i is another zero. Notice these imaginary zeros come in pairs, one with a positive I term and one with a negative I term, one with a positive I term, one with a negative I term. Imaginary numbers always come in pairs like that. So, you try the next example in part B.